Welcome back to The Explainer. Today, we're diving right into a real mathematical detective case. Now, if you've been working with calculus, you already know it's an absolutely fantastic tool for finding the exact slope or the rate of change of a function at any given point. But what happens when we need to find the slope of wild, complex mathematical shapes that flat out refuse to behave like standard functions? You know, the shapes that loop back on themselves or cross over their own paths? Well, today, we are unlocking the secret to solving those impossible curves.
Here is our roadmap for today. First, beyond explicit functions. Second, the chain rule connection. Third, the four-step strategy. Fourth, tangent lines on curves. And finally, mastering implicit differentiation. Let's start with section 1, beyond explicit functions, when curves break the rules. So we have to start by asking a pretty fundamental question. What do we do when our normal calculus rules just hit a dead end? Consider the contrast between these two completely different mathematical worlds. On one hand, we have an explicit function, like y equals x squared plus 1. It's neat, it's tidy. The dependent variable y is completely isolated on one side of the equal sign. It's entirely defined in terms of x. If you want the derivative, you just use the power rule and you're done. Easy. But on the other hand, we have an implicit equation, something like x squared plus y squared equals 25. Notice how the variables x and y are just scrambled together? Y is no longer explicitly given to us. It's implied. It's hidden within that relationship. And that scrambled relationship illustrates exactly why these implicit equations cause us so much trouble. Take that equation, x squared plus y squared equals 25. That creates a circle with a radius of 5. But think about how that circle behaves. It fails the vertical line test. A single x value gives you two entirely different y values, one on the top half of the circle and one on the bottom. Because it fails that vertical line test, it's not a single function. And that means our standard explicit derivative methods, which totally rely on having one clear output for every input, completely fail to work here. Moving to section 2, the chain rule connection, the secret weapon. Okay, so how do we actually find the slope of a tangent line on a shape like a circle? The crucial thing is understanding the core algebraic hurdle standing in our way. If we want to find the slope of a curve, we have to find dy over dx, the change in y with respect to a change in x. But if y is all tangled up inside an equation, say as a y squared or a sine of y, how on earth do we take the derivative of y with respect to x when it's not an x? Well, the answer is the chain rule. We basically have to treat y as a hidden function of x. Imagine y as a closed box. We know there's some mathematical relationship to x inside that box, but we can't easily unpack it. So when we differentiate an implicit equation, every single time we take the derivative of a term with y in it, we apply the chain rule. We take the derivative of the outer layer first. For example, if we have y squared, the derivative of that outer layer is 2y. But then, because y is a hidden function of x, the chain rule dictates we absolutely must multiply that by the derivative of the inside. We multiply it by dy over dx. So the derivative of y squared with respect to x isn't just 2y. It becomes 2y times dy over dx. That little dy over dx acts like a tracker, popping up every time we interact with y. Section 3, the four-step strategy, the master blueprint. Now that we have our secret weapon, it's time to look at the definitive four-step strategy to crack literally any implicit differentiation problem. Honestly, I want you to memorize this mantra. It's a permanent cognitive hook that will never fail you. Ready? Differentiate, move, factor, solve. Step 1. Differentiate both sides of the equation with respect to x, remembering to use the chain rule on the y terms so your dy over dx trackers appear. Step 2. Move. Use basic algebra to move all the terms containing dy over dx to one side of the equal sign and just shove everything else to the other side. Step 3. Factor. Because all the terms on one side now share a dy over dx, you factor it out like a common multiplier. And step 4. Solve. Divide both sides by the remaining algebraic expression to get dy over dx completely by itself. It really is that simple. Differentiate, move, factor, solve. Let's look at section 4, tangent lines on curves. Solving the case.
Let's take our new master blueprint and solve a real, beautifully complex case. There is this incredible curve called the folium of Descartes, which translates to the leaf of Descartes. It features this really elegant loop in the first quadrant that crosses over the origin. Its equation is y cubed plus x cubed minus 3xy equals 0. Try isolating y by itself in that equation using standard algebra. Go ahead, try it. It is practically impossible. But what if we still want to find the exact slope of a tangent line touching this leaf?
We don't panic, we just use the blueprint. Step 1, differentiate both sides with respect to x. We're going to apply the derivative operator, d over dx, to the entire left side, which is y cubed plus x cubed minus 3xy, and also to the right side, which is just 0. And here is the secret weapon in action. Taking the derivative of y cubed gives us 3y squared, but because of the chain rule, it sprouts a dy over dx. The x cubed behaves normally and just becomes 3x squared. Now, the 3xy term requires the product rule. Treating 3x as the first part and y as the second, we get 3y plus 3x times dy over dx. Setting that whole derivative expression equal to 0, we have successfully executed step 1. Notice how differentiating the y terms literally scattered those crucial dy over dx components throughout our equation? From here, we basically just turn the crank on our algebra machine for steps 2, 3, and 4. We move the terms without a dy over dx to the right side, we factor out the dy over dx from the terms on the left, and finally, we solve by dividing. When the algebraic dust settles, we get this really beautiful, neat expression, dy over dx equals 3y minus 3x squared, all divided by 3y squared minus 3x. Notice that our slope formula requires both the x and y coordinates to work. Which actually makes perfect sense, right? Because for a shape that loops over itself, an x-coordinate alone isn't enough to tell you exactly where you are on the curve. And this is where the math really comes to life. If we want to find the tangent line at the very tip of the leaf's loop, let's say at the coordinate 3 over 2, 3 over 2, we just plug those numbers right into our new slope formula. The math works out perfectly to -1. And if you map it out, that straight tangent line brushing past that exact point clearly has a downward slope of exactly -1. We solve the case. Finally, section 5, mastering implicit differentiation, bringing it all together. Think about what we just did. We took what could be an incredibly frustrating algebraic chore and transformed it into a highly logical, step-by-step tool. Implicit differentiation unlocks the ability to find slopes for complex curves that completely fail the vertical line test. The chain rule is the mathematical key that makes it all possible, acting as a tracker for the hidden variable. As long as you memorize the 4 steps, differentiate, move, factor, solve, you literally have a calculus superpower that is absolutely essential for advanced physics, engineering, and geometry. Which leads me to leave you with this final, kind of wild thought experiment from our source material. Imagine a video game where a rocket travels in an elliptical orbit, defined by the implicit equation 4x squared plus 25y squared equals 100. The rocket needs to fire a missile along a line tangent to its orbital path to destroy an incoming asteroid. With the exact tools you learned today, you actually know how to calculate precisely where that missile will go. You just differentiate implicitly, find the tangent line, and track its intersection. Who knew that mastering the chain rule and a simple 4-step blueprint was the secret to saving the digital universe? Think about that next time you look at the complex curves in the world around you. Thanks for joining me on this explainer, and I'll see you next time.